Hi, and welcome to another episode. This is episode 2 in my series of all you never wanted to know about the C-64 Power Brick. And even though you probably learned more than you wanted to know in the first episode, we are going on. This guy just keeps rambling on and rambling on. And this time we are continuing with the Power Brick itself. And please be warned, for those of you that don't like to watch surgery, in this episode we will be cutting open and gutting the inside for some C-64 Power Supply. So be warned, they are not killed, they are good taken care of, and they will be put into action again after we have put in some new internals. But the main power supplies, they will remain the same. And the power supplies modification themselves will not be this episode, so there will be a third episode in this series. But now let's just continue a bit with theory before we go to gutting and measurements. Yes, what a waste! That was what we stopped our last episode with, and we are going to start here today, because we are going to identify where power is lost. Why is a power supply getting warm? An idle power supply should be cold as ice, because it should generate no excess heat. All the heat that is made in a power supply or in a cable or whatever, it's loss in our terms. And where can this waste of power occur? We have several places where this could occur. We have the cable, we have the transformer, we have the rectifier, we have the regulator, we have the cable, and we even have the connector on the C-64 side, like so. And we even, between these, have the fuse. Every one of these is components that are getting hot. They will take away some power. And if we just concentrate on these ones, where we have the biggest loss. And this cable loss we are actually measuring now just from the main, so we can ignore this. This is a very low power draw unit. Of course here, this cable is more than 1 meter long and you have a connector with not the best surface. And 1 meter of this cable is about 0.00175 ohm. And when you have 4 leads, you have about 4 times this. But it still will be about 0.007 volts approximately drop on both. It's no big deal. We can ignore this on this side. So we are going to concentrate on these sources for loss of the power that we are putting into the unit. And this is also why things are getting warm and destroyed, is because of the waste of power in these units. And the transformer, we identified this last time, and we can see that this is a picture of a transformer. This is not the C-64 transformer, it's any transformer. And since we don't have any rating of this transformer, we state that it's about 95% effective, and we have about 5% loss. And the loss in watts is of course a function of how much current that is drawn in this. So it's 5% of the total power that is drawn from this in watts is the loss that will occur inside the transformer. And in the transformer we have the efficiency of the core of the transformer and the magnetic field, and we also have the winding loss, that is the resistance that you have in the length of copper wire that is in a transformer. And of course the thinner the wire, the greater the resistance. So you have these. This is the magnetic field in total transformer efficiency. This is the core losses, and this is the because of the windings. So in effect, all of these says that the transformer is normally, I say 90%, but 95, 90, it doesn't matter much with these small currents. And if we put some numbers into this, we see that if we draw the total amount of power that you are able to, if you follow the instructions, you can see that 5% state that the transformer produces 1.22 watts of heat when the total power is drawn here. And of course, we do have some other measurements in here that state that this is a bit higher, but it's still below 1.5 watt with the nominal current draw. And we do have a rectifier here, and some people say, but there is no loss in the rectifier. But of course there is, because these diodes are getting hot and they have a voltage drop, and everything that passes a current and has a drop of voltage do produce heat. They do have an internal resistance, and in case of a diode, this is a very explicit and both measurable, and we do have data sheets that explains how much this will be. And a normal rectifier diode, you can count this about from 0.7 volt to 1.1 volt over each diode. And in this case, we do have two diodes in series effectively. So if we take this carefully and we are measuring with RMS values, we should get approximately a result that is between 2.7 and 3 point something here as this loss. So it's in that area. We can say for now that is 3 watts that is lost in the diodes. And there are some measures you can take to reduce this. You can use more expensive diodes, but do remember that Schottky diodes and stuff is not very good for low frequency rectifying. And when it comes to this, we will see that this 9 volt and 12 volt AC, that is the numbers we have used. It's not very accurate. And then we come to the biggest loss, and this is the loss that is done in a serial regulator circuit. And to find out how much we actually are losing here, we do have to break open a C-64 power brick and do some measurements, because we need to measure the internal voltage that is here, and the voltage that is here is given, it's 5 volt. So this one here, we actually can derive from the difference between this voltage and this voltage. But in effect, when we are doing the calculations of the loss, it's the voltage from the input here to the output that gives us the exact voltage that is dropped in this circuit. The power we know. The power is what is passing through the load. The other EB that is passing here is very small. So let's just ignore this, and this is different from every regulator. And in the Commodore regulators, it's a bit bigger than normal, because this is a generic way of putting how these serial linear regulators actually act, but they have a lot of internal circuitry to do current limiting and security functions and stuff. So this is basically how a C64 actually looks in regard of the voltage. And I do always find some variants of this. I think I have seen 10 different versions at least. But in effect, to raise the voltage over the 7805 regulator, they are putting a bias up here on the earth pin that also will drain some power in this resistor network here. But this is small when it compares to this, so we just choose to ignore this. But in reality, E out is this current here that's passing down here, plus this current that is out here. It's an example of Kirchhoff's law. And it's really the same with this. Here we have also drawn in just a diode circuit to see how this should be done, because you have no power indicator on the C-64 power supply. And power is always the product of the voltage that is measured over a device that is passing through current, or letting current pass through. So let's go and break open some 64 power bricks, shall we? As you can see, it's still winter here in the north. Actually, it was a lot of snow now in the south too. But I'm going now into my outer garden shed, where I keep all my stash in the winter. And here I also have a small bench for doing dirty work. So let's break these bad guys open. This is not going to be some in-depth video about how you in detail break these free, but I'm going to try some things here. These I have often fixed, and they are not hard to take apart. These I had some mixed experience with. This is a 89 model. This is working fine, by the way, through all normal measurements and stuff. But I'm going to show you what it takes to break these free. And this is the same with most of melted plastic stuff. You do need some way of forcing them open and break the initial glue that is surrounding this. And if you use a woodworking tool like this that is kind of broad, it often breaks the glue without breaking some plastic. So it's just some light tempering around the edges. Let's put this in the vise like so it's not going all over the way. So it's not going all over the place. You can hear some glue breaking away, but it's not popping open as of yet. And I know this kind of video is not always very entertaining, but I do like to show things to get a perspective of how long time things take. So I have not cut into this. This is the whole footage of how long time it took to break open these covers. This plastic is not so very brittle, but you can see here it is, yeah, kind of difficult to get it away without breaking anything. But on these power supplies, my experience is that it doesn't matter that much if you break something, because you have to use a lot of force on the ones I have seen so far to be able to do a good refurbish. It is by the cable, so it's good not to damage the cable. And since it's not the same on all of these, it's difficult to know where to break. It's much easier on the foot warmer power bridges. Yeah, you can see here, this was the kind with also with feet, but you can see here it's kind of tight packed with the epoxy. And you can see the mains coming in over here, and that is where the transformer will be. And you can actually hack this out. I've seen people actually remove all of the goo in these ones, but it's tightly packed. It's a real yeah, it's a real problem to fit anything more inside here without breaking anything. And there actually are someone that has made an extension that you can put on the bottom here, like 20mm up, that you can use to refurbish these with just bypassing. You cut the wires here and you have the extra room to refurbish this. We might look into that, but first we are going to look to a classic power bridge. And these classics, they do have some plastic fingers that is going into this, and sometimes you are able to break them free, sometimes you just tear them apart. But anyway, it is quite easy to get the lid to stuck back on with glue. But I will do the same on this one. Just hack easily around the perimeter here to see where it's stuck. And probably it is just the plastic standoffs. more irons. It was loose from this side, but this plastic standoff that is glued into the epoxy here, if you are not careful, you can just use force and break them straight off. In some cases that is the easiest thing to do and do the least damage, but of course then you have to glue them back on. You can see here in the plastic where it's stuck. But I'm also going to check here around the fuse hole. You can see this is one that is probably started its life. Actually, I'm not so sure about this one. It does not have the Norwegian Nemco mark on it. So this might not have started its life in Norway, but it's exactly the same. And I do think it has the fuse on the primary side, the hot side of 220 volt, and then it's okay by Norwegian standards. Now I have broken off most of the plastic that keeps this lid secure, and of course I have to be careful not to damage the internals here, but it's just a small piece more of this holding it in place. Just going to smash that plastic oiler inside here. You can see here where I broke it off. It's this one here that is melted into this or glued into this this epoxy, and I just broke it clean off here. And otherwise you have this standoff, this plastic here that is glued on these sides. But when you glue this back, we just clean up and glue it to the perimeters here, so it's not a very difficult task. And inside here you can see you have a classic PCB, and this PCB contains the regulator that we need to get into. And I will do some, try to get out some of this epoxy, and might show you that. But today I'm going to do the measurements with one of these power bricks, so that we get the basic gist on things. Oh, this cable is getting stiff in the cold. It's quite cold in here. As of now it's about 4 or 5 degrees Celsius inside the shed here. And inside this wall here I do have my garden shed, where I also do some filming and stuff in the summertime. But now let's take this inside, do some desoldering, and see what kind of voltages we have here. Yeah, as you can see, these power bricks are really not that hard to break open, and I kind of wince every time someone tells that, just toss them in the bin, they are useless and you should never use them and it's a waste of time to modify them. but that is utterly bullshit. This is easily adaptable to modern needs for a C-64 power supply, and by getting rid of the series regulator, we actually can get a very good power supply on this. And you can see the points where this actually is fastened. You have these two wedges here that goes into this corner. These I almost always break off. I think once or twice I've been able to save them. There are some glue here in these points, and there are some glue around here the corners, and especially on this front here there used to be glue. And you also have the points here where you have these pins that is stuck. These pins are just stuck into the epoxy, and these pins here have a hole inside here, and they are just glued with about the same glue or epoxy. And they call this epoxy, but this is actually a sort of thermal compound because it's almost impossible to melt. It takes and absorbs heat very, very good. So this is a very good way of transporting heat to the outside of the brick because it's heat conductant. And you can see all this available space you have in here after you have desoldered the regulator. This is not the regulator, in fact, it's the rectifier and filtering capacitors and sometimes some resistors that are on this PCB. And here you can see that there is some aluminium heat sink in here that is enclosing the transformer. And this regulator down here is fastened to this aluminium, and it dissipates its heat through this. This wedge here is of course also connected to the plastic, and here is the one that I had most resistance, and this is where I cut with the chisel last. It's I've never got this out of the epoxy, so you always have to trim this apart. And this also acts as a shield for the high voltage side that is here and the low voltage side that is out here. So it has more than one function. It's not just to secure the lid in the middle of the desert here, I was about to say, but it's also doing shielding high voltage to low voltage. Yes, we're back here at the bench, and we just did break open this one. And what we are going to do, we are going to check what voltages these have, both with open pins and with about maximum power draw, and yeah, a power draw that is about what we measured last time. We are also going to look into what this actually contains when we have desoldered the pins from this one. For now, I am ditching this one. There are some narrow wires here that is not supplying the full current without keying, and it's too much plugs. So I have actually gone overboard and designed this. Or designed, this is just a cable. This is a supply cable for putting into your C-64, where you can actually supply the voltages inside, and these two are the AC voltage and the ground and the plus 5 volt. So you can use your auxiliary power supply and supply this. So that of course I can do, but I've also made the opposite part where I plug in my power supply, and I do have these in the other side. So if I'm just going to use this as a piece for measuring stuff, I can just connect these like so, and it will be a pass-through wire. And this is half, I think 0.5 square cable. I'm not totally sure how this is. In Norway we call this in the area of the copper inside. So this is 0.5 millimeter, square millimeter, like so. And that will be enough not to get much draw here, but of course these can introduce some noise and stuff, but this will be a far better solution than what we did last time. And to supply what I did in here with these resistors, this is not a maximum load. So instead of doing that, I have these resistors here. These are 4 or 5 watts, and these are 15 ohms each. 3 of these in parallel, and I will have about 5 ohm, and that is 1 amp on the 5 volt rail. And I take one more of these, and I will get 1/4 of 15 ohm on these, and they will supply maybe a little more than 1 amp over the 5-volt rail. So that will be a very good load to make a good simulation of this. And these are 5 watts and 3.3 ohms each. So together these will be about 10 ohms and 15 watts. So I'm going to connect these ones in a series and these ones in parallel. And I'm going to connect them to some banana jacks so that we can just hook them up and connect them to these. So that's the first line of business. And you can actually use these power resistors and overload them even more. You can put them in a glass of water and have them water cooled. That is one way that I have used many times when I need to test something under load. But these alone should be good enough to give us what we need here now. I'm wiring these up so that I can reuse them to other things. I do have some old stash like this, but of course, as I'm doing experiments like this and never cleaning up and using this, they are getting more spares. I used to have about 3-4 kilos of power resistors just lying ready. And these I'm just going to connect in series, as I said, and that you're just doing it like so is an extra security, because if it gets too hot, they just melt a bit so that they get apart. I think when these get hot enough to melt the solder, then the C-64 PSU has got enough load, just like so. And just connect this to some 4mm lead. I'm actually getting very few of these two left, so I didn't find the ones I should use for this, but I do think it will actually clamp on this one. Yeah, I give this some solder too. It's easier to make it fit inside there. Actually, I'm going to take this the whole 9 yards, like so, and do like this. So I'm sure I'm got a good connection inside here. And of course, using solder on contacts like this that is potentially getting hot, that is not always a good idea, because the solder will actually melt and welding together. So you should not use welded contacts normally when you do fit pressuring, but I tend to do that anyway, and in most cases you get away with it. And no, I have not done any control measurements of these resistors, and of course they are not the most accurate thing in the world, so we can try to check what Mr. Fluke tells us about this story. And we can check here on the points, 10.4 ohms, and that is actually not bad. Yes, and then these fat boys here are going to get a totally different connection. I was not thinking of soldering these, because I might have to take them apart to make different kind of loads on this. So I was just thinking of doing like so, where I just clamp them inside this plug here and do the same on the other side. This is meant for speaker wire, but we don't really care, do we? Here we have 1/4 of 15 ohms. We see what that gets in real life. 3.8 ohms, and 3.8 ohms. If we do Ohm's law on this, it will be like so. So that will be the current, and this is a very good estimation of the highest load we can expect. And of course the about 9 to 10 volt of the AC voltage on a 10 ohm resistor will be as close as we can get. And let's see about the wattage on this. It doesn't matter if you connect these in parallel or in series. It will be the same effect on each or watt on each of these. So these will take 5 watts each. So this is able to draw 15 watts without getting destroyed. And these will actually be able to draw 16 watts without getting destroyed. So in total we are able to put a load of about 30 volt amps on the circuit with these ones. And that is actually what we are going to do. But first we do have to destroy our C-64 power supply even more than we already have. This one actually looks in really good condition. It has not been much used over the years, so this is not the worst example I've seen. And this is normally coupled so that these ones are the earth wire, and these are the plus 5 volt wire, if I don't remember wrong. And you do have, this is connected to one capacitor, or was it? No, this is connected to the windings. Yeah, this is the windings from the transformer, and this is the voltage regulator. Yeah, we do have to see when we get this apart. Yeah, we can use some desoldering wire on this. This is very good soldering on this one, so it's easy to draw the solder, and it's one side only PCB. This is tinned PCB also, so I do get a lot of solder to suck away with this, but it's doing the job rather nice. There's one loose and there's one loose. And then it was this voltage regulator thingy. It's also loose inside here. Okay, so this PCB is exact one I've not seen before. They're actually using a sturdier rectifier than I've seen before, and it's using a tantalum as the noise suppression, and this is the 4700 microfarad 16 volt. This is not the best capacitors in the world. It's made in Germany, and you have the minus and you have the plus. This rectifier bridge kind of thing I have not seen before, but we are going to look this up and see how much voltage it really can take. So what we do have left here in our power brick now is actually quite easy. You have this winding out of the transformer that is supplying the AC voltage. We do have this wire here. This is the yellow one, and we do have the brown one down here. These are connected to another winding on the transformer. So these are the 9 volt AC, and these should have the DC out to our C-64. So if I'm going to measure out how much this can supply me with in AC voltage, yeah, I actually can do I can just solder this in place again and do some tests inside the power brick, or we can do the open tab on this now. Yeah, we do the open measurement first. We can do that when this is flying so in the air. And this power brick is of course supplied with power at once, and you do have different kind of these plugs. This is one of the sturdier one, and I'm going to use part of my connector here, where I have this one that I plug into here. And now it was about measuring open voltages on both these rails, and we are going to measure AC here and we are going to measure AC here. Just open voltage from the transformer. So open 9 volt and 5 volt unregulated. And I'm going to use both this and this one to measure. Now I'm first measuring the voltage on the 9 volt rail, that is the actual output, and this is the one here. And I'm also going to use my fluke as the secondary measure point on this. And I'm just going to plug in the power brick AC mains, and be careful. You have to know what you are doing when you are using open circuits like this. And on this one you can see that it's having peak to peak voltage of 30 volts, and it do have then an amplitude each way on about 15 volt, and this is open clamp peak to peak. Peak to peak it's 30 volt, and let's see what the fluke has to say about the RMS values of this. 10.74, that is about the same as we measured last time on the other power supply, and this was with open. And if we take the load into consideration, what will happen then? And I'm going to disconnect this now, and this is our load. I'm going to put it on some something that is distancing it somewhat from the surface. So if something burns, it will be something cheap, I hope. So now the load is connected. We have it lifted from the ground, and this was a 10 ohm resistor on 10 volt RMS, so we should got about 1 amp through this, and 1 amp on 10 volt should be about 10 watts. So let's hook it up. Oh, we run out of power on our multimeter. I do have to connect this to power. Yeah, let's try again and see if we have better luck with some juice into the scoop here. Sorry for the glare in the screen of the multimeters, but I didn't really notice this, and I couldn't really fix it either with the lighting I have. Yeah, let's hook on some power. The load is still connected, and we can read out the values we have here. The peak to peak is now 28 volts, and the RMS is, if we check quickly here, 10 exactly, 1004, 10 volts on the AC, and that is of course the same we are measuring out here, 10 volt, yes. So 10 volt is going 1 amp on the AC voltage rail now, and we are going to clamp in the other load on these pins here to see what we get, and then we need some hooks and grabs to connect this, because this load here is connected to these banana jacks, and these cables might get a bit hot. I'm not sure how they will take the pressure, but if I connect this one here, I use different colors here, this one like so, and the load here will be connected like so and like so. And what voltage do we have now on the open clamps of the AC voltage, on the closed clamps I mean? If I take now the scope probe and measure on the output here, I will get about 26.5 volts. Actually, I did this wrong. This should be 28 and this should be 10 volt. And what I'm measuring here is with load 26 and RMS. On these I do feel that they are getting hot, 9.9 volts. And let's measure this without load. I disconnect here and take this clamp like so. Then I have also on this one 30 volt and RMS. The RMS value on this one, the RMS value will now be 10.7. That means actually that the two windings on this transformer here actually are the same on both sides. Maybe a bit thinner winding on the other, but I don't think so. I think this has two windings that are able to deliver about the same. And now the heat is getting kind of hot here, but I will connect this again to the load. So now I have a fully loaded C-64, and I'm going to try to measure how much power draw we actually have now on the power cable into this power supply. So if I use my meter here and measure on the intake here, I have about 140 milliamps. It's actually 160 if I clamp it together as it should be in. So this is on the primary AC side, and we can check now with this meter. No measure on this one. This is the 5 volt. It actually states that this goes 2.4 amps on this, and we are overloading these resistors quite much. And this one I do have 0.92, 2.92 amps on this one. Yeah, I will write up these measures in a table, and we will connect the old board in here, and I will measure again. What I have done now is that I've put the PCB back in the power supply, and I've attached some leads here to be able to measure on a bit easier terms here. I do have this scoop probe. It actually was melted into the plastic. I did this on the 5-volt rail. This actually melted into this, so it's not working as good as it used to be. I may be able to rescue it by doing something with the plastic, but I'm keeping this on this output. This is the output, and I have not connected anything to these yet, but I will connect one wire from the ground here to this so that I have a fixed ground. And now we have no load connected to the 5 volts, and I have no load connected to the AC. So this is open clamp again, open clamp, and with this regulator. And now I put the voltmeter in DC, and we measure the input is 13.85 into the rectifier. 13.5 into the regulator, and that is out from rectifier. And if I measure here instead on the output, I do have 5.1 volt. And if we see here on the scope, I have about 25 millivolt with ripple, because I have a minimum. It's not that much actually. It's 4.99 volt output I'm measuring on this one, so it's maybe a bit more bad contact in my measuring points and stuff here. But let's now connect the load to the 5 volts, and now our load won't get as warm as it was earlier, because we are only going to attach it with the 5 volt, not the fully 10 volt that we did earlier. And this load here we actually just can connect up to our cable straight here, and I will piggyback this to the ground. So now it will load this with about 1.3 amp. We can check with our amp meter, put this on DC and see what we have into the load here. 1.44 amps. That's a perfect maximum load. 1.44 amps. And what voltages do we have now on the output? 4.97. We have not much more ripple than we had earlier, but a bit more. And we had about 5 volt fully loaded, 4.99. That is as good as 5. And now things are getting hot inside here, because we are drawing the maximum load of this regulator. And on the input for the regulator now, it's 11.12 volt. So it's going down from 13.5 to 11.4, 11.1. But then I will be able to measure how much is wasted in this regulator. But I will just turn off this now before I break anything. And I can of course also measure again to make sure that this is linear and not increasing. So it's about 1.44 amps. So we do have some inaccuracy in this. We do know the voltage and we do know the resistance on this. So we will be able to do a very good calculation of what the current actually are here. So then we disconnect and we can actually take this apart again, because now we are going to try to measure with some modifications to this power brick. And here is what we found out when we was doing measurements. We did measure with open circuit. Open circuit is when you leave the windings open and have nothing attached to them. The multimeter is very high resistance and doesn't put the load on the circuit. And as we can see on this power brick, there are two almost identical rails. So the 9 volt rail and the 5 volt rail, or the one rail that is supposed to supply the 5 volt, they are the same. Because with the other power bricks that has two windings on this 5 volt rail, it's a bit different. But on this one, they just are the same as this rail. Maybe there is some thinner wire on this, maybe there is not. I'm not totally sure. And I was loading this with the resistors 10.3 ohms and 3.8 ohms. And I did measure the voltage, and this is RMS values. And RMS values is where you take into account the shape of the actual curve that is measured, and it's measuring every piece of voltage that is going up here. So if you do have a sawtooth like this, it will measure both over and under and take into account the shape of the pulse. So we are measuring with RMS, its absolute values, and we are also measuring current. And in the first instance, I connect the 10.3 ohm resistor just straight to the 9 volt rail, and we can see it drops somewhat, about 0.7 volts, and it's supplied about 1 amp with current. And when I did this, I connected the 3.8 ohm resistors, and you can see the voltage drops from 10.7 to 9.9 volt. That's a drop of 0.8 volts. And we actually draw 2.61 amps in this configuration. We didn't have it on for long. Both the resistors and the power supply is a bit overloaded with this. But no big deal, because the transformer is kind of self-regulating on this, and it didn't get warm. It did get somewhat hot to touch, but not overly hot. And I measured both this with a desoldered regulator board and with the regulator board installed, and that is to get the power out of the 5-point rail as it is regulated. And with maximum load, you can see that the drop was to 4.99 volts, and then we draw about 1.31 amps out of the circuit. The AC was about the same, and then we experienced that we have a total regulator loss of 6.43 watts. And there are very little sources for measuring things wrong here. And I also measured the AC voltage twice, and it was between 2389 and 2384 and 2386 in that regard when I was measuring. And this is what we really did when we had the open circuit and the loaded circuit. We was just measuring on each of these rails. And you can see one rail is here. This is the 9 volt rail. It's going straight into the transformer with the yellow and brown wire. And you have the other windings are coming out here straight as copper and go straight to the board, and is supplied into the cable for the C64 through the white wire that is plus and the green wire that is the earth or minus. And we did find out some more, of course. Because we measured now on the input and the output, we was able to calculate what the loss over the regulator was. And 4.99 is 5 volt output, and the 5 volt rail into this was 9.99 volt something. So it's almost 5 volt drop over the regulator as it's calculated here. And that means that you have a regulator loss and a supplied load that is almost the same size. So half the power that goes out from the transformer is actually consumed inside the foot warmer power bridge and gives it a good and warm feeling, because it's supplied with 6.5 watt with heat just from the regulator circuit, this one here that is supplied to this heatsink alone. So this regulator is losing half the current that it actually supplies out of the circuit. So what have we learned so far, and what are the implications of this? The 9 volt rail, we can just ignore it. If you see here, the 9 volt rail is just passing out straight to the cables here, and it's no concern at all. And if we agree on the fact that we need a 9 volt IC voltage to supply something inside our C64, which we really don't, but if everything should work as it should, we do need an AC voltage inside. So we do need a transformer in our circuit, and then this is just fine. We have already established that the transformer is about 95% efficient anyway. And we have established that the 5 volt rail have loss in several parts of the chain. And the biggest one of these is the diode rectifier bridge, that is about 3 watts. And the liner regulator is about 6.5 watts. And of course the transformer is 1.5 watts something. So we can really just ignore it for now, but we will take it into account anyway. So what if we increase the efficiency of the rectifier and the regulator of the foot warmer as it is? And this is why we never should toss away these power bricks. We know that this is 32 volt amps maximum. It's stated on the backside of the brick itself. And we ignore that volt amps and watts is really not the same, because to calculate this you have to take into account that the voltage and the current and the consumption of power is not exactly in phase when it comes to AC voltage. But just ignore this. So we are going to use watts and volt amp interchangeably here. Full loads on the 1 amp on the 9 volt rail is about 10.5 volt amps, as it is on this transformer what we have measured. And this is because this is really 10 volt AC rail. And that leaves us with a power budget. Here we are using 10.5 volt amps of the 33 that we do have in total of this. And that means that we can say that we have 22 volt amps left to spend. So that means 22 volt amps minus the transformer loss, minus the rectifier loss, and that means that we have ideally 3.5 amps that we can draw from this 5 volt rail. And that is really much more than the 1.5 amps that is stated on the backside. But we will lose something even in a modern regulator. And with a serious regulator, it's not possible to supply this anyway, because you do have to have some overvoltage, and this overvoltage is too big to have an efficient regulator. If this overvoltage was not 5 volt but just 2 volts, it will have been much more efficient. So what can we accomplish with the modern technology? You know that it's possible to buy all these small circuit boards from Asia, and we are going to show that. It probably will be in the next episode. But if we look into the data sheets of what can be established with a more modern replacement, this is not by any means a drop-in replacement. You have to have some circuitry around it, but there actually are someone that are making drop-in replacement based on this circuit here. But you can see that the efficiency of this, I actually marked this wrong, I see. It's the 5 volt that we should use, not the 3.3, so it's actually up here. I'm sorry about that. So that means that what we are taking into account, we are getting 5 volt out. We are supplying this with about 10 volt in. And then we have an efficiency here that it's about 88%. And the same on this one. I've also taken this into... I'm not sure why I've done this. I must have been tired, because this one should leave this little delta up here. That should leave us about 88% efficiency. But there are some other losses that probably are not taken into account here. It's better to be safe than sorry. So I'm saying that we are going to say that these kind of circuits can be about 82% efficient. And we did remember that the circuit that was inside now was only 50% efficient. Yeah, but so what? Yeah, we do have that with 82%, or we can first take the ideal solution that we had from the other sheet is 3.5 amps. And with a modest 82% efficiency, we can get 3.5 amps times 0.82. And that is a 2.8 amp output. And that is significantly better than the 1.5 that is stated on the box. And all this we can get with just making the power brick cooler than it is today. So in effect we are almost doubling the potential of the foot warmer, and it will actually be able to power a C128. I would not recommend it, but it is possible. And that makes it madness to toss away these power bricks. The white ones, it's much more work, but these brown wedge-shaped ones, you need to keep them. They are worth money. If you are going to buy the same kind of transformer today, it will cost you around 300 kroners or something in Norwegian money for the simplest one. But that know-it-all mansplainer, how can we know that he's telling the truth and not just rambling around as he used to? Yeah, but I did a control on these totals when I loaded with the total maximum load. The input mains is 228.6, and I was measuring 150 milliamps when I was doing the internal regulator board installed, and 160 milliamps without. And of course this is because the higher current draw we have with supplying 3.8 ohms of resistors to 10 volt instead of 5 volt. And the total supplied power into the system was then 33.4 volt amps with the regulator board installed. And that's not far off from the 33 volt ampere rating. So we know that this is able to supply that with no questions asked. And without restrictions, when I didn't have the regulator board installed, it actually delivered 38 volt amps, or consumed 38 volt amps. And the transformer was getting warm, but only comfortable warm. It was not hot to the touch. So it was not, you would not be alarmed over power supply that was this hot. And remember that the heat inside the brick are only about 1.5% from the transformer. Oh, this is wrong. This is 5%. This is a typo, sorry about that. The heat inside are only 5% from the transformer. You remember the transformer was about 95% efficient. So the rest are the about 10 watt loss in the rectifier and regulator circuit. So we do know what we need to fix. We need to fix the power regulator circuit, and we might have to do something about this rectifier diode, but there is a very minimal, you can gain by doing a change of this bridge. So what are we going to do next? Yeah, we do know that this is a really good power supply in theory. And we need to try this with another power regulator to see how it delivers then. So I do think that will be the topic for the next episode. Yes, that was it for this episode. We do have learned something. This was very throughout explanations of everything, I hope. There still are some bridges to gap, but the next episode will be explaining a bit why switch mode power supplies are more efficient, and we are going to, I won't say replace, but it's only the regulator that we replace. We can actually use this card that was there from before, but I will replace at least the capacitor here to make sure that it doesn't get destroyed in the process. But this capacitor is actually working quite good. We did load this with 1.5 amps and there was almost no ripple at all, so the capacitor is actually working. But enough of that. Next episode will be 1 or 2 weeks. I'm not really sure. It's a lots and lots of work doing these in-depth videos. I need to make sure that all the calculations and all the other stuff are correct. And even though I don't do any manuscripts when I make movies, of course, this presentation that I do throughout this video instead of showing my face is it's a lot of work putting together. So I hope you enjoyed the contents. Please leave a comment below. Please share this. This is guaranteed the most in-depth knowledge out there on the C64 power bricks. And hope to see you in the next one. And don't forget to watch some of my older and other videos. Thank you for watching.